Welcome. You ever stare at a physics problem, you know all the formulas, but you just feel like you're missing the key? Well, today we're going to unlock one of those puzzles, problem 1.167 from the legendary Irodov collection. It's a classic collision problem, and trust me, by the end of this, you're going to see the physics behind it in a whole new light. But before we even touch the math, let's start with this big, kind of paradoxical question that's at the heart of our problem. We're always told that energy is conserved, right? It can't be created or destroyed. And yet, in any real-world collision, think about a car crash or even just dropping a glass, it sure feels like energy is lost. So what's really going on? Where does it actually go? All right, let's get into it. Here's the challenge. We're tackling problem 1.167. Now, don't let how short this problem looks fool you. Every single word in that statement is a clue that we're going to need.
So the problem asks us to find the increment of kinetic energy. That's just a fancy way of saying the change in energy. And it specifically points out that this is a perfectly inelastic collision. Honestly, those two phrases are the whole puzzle we need to solve. Our goal is to find a single value, we'll call it delta T, that tells us exactly what happened to the energy in the system.
Okay, so before we solve any physics problem, you gotta know which tools to pull out of your toolkit. For this collision, there are two key physics principles we absolutely have to understand. The first huge clue in the problem is that phrase, closed system. This is basically the author giving us a massive hint. It means that there are no outside forces messing with our two spheres. And in a closed system, one very, very important thing always stays the same before and after the collision: the total momentum. And clue number two is perfectly inelastic. This isn't just any old collision. It's a very specific kind where the two spheres actually stick together after they hit. Imagine two lumps of clay smacking into each other and becoming one. This is so important because it means that after the collision, we don't have two objects anymore. We have a single object with a single final velocity. Now this right here, this is the trap. This is what gets so many students. If the total momentum is conserved, it just feels like the total kinetic energy, the energy of motion, should also be conserved, right? It seems totally logical. But it's not, absolutely not. And this slide shows the single most important idea for this problem. Over on the left, you've got an elastic collision. Think of billiard balls. In that perfect world, both momentum and kinetic energy are conserved. But on the right, in our lump of clay scenario, the perfectly inelastic collision, something else happens. Momentum is still conserved, yeah, but kinetic energy is not. That energy has to go somewhere else. So now that we have our tools, we can put together a game plan. We're not just going to throw a bunch of formulas at the page and hope for the best. We need a strategy. Let's see how we're going to build this solution. We're going to follow a simple three-step strategy. First, we'll use that conservation of momentum rule to find the final velocity of our stuck-together spheres. Second, we'll write down the formulas for the kinetic energy both before and after the collision. And finally, we'll just subtract one from the other to find our answer, that delta T. This little roadmap is going to make sure we don't get lost in all the algebra. All right, time to execute the plan. Part 1, solving for that final velocity. Everything else we're going to do depends on finding this one value. So let's make sure we get it right. So before the collision, the total momentum of our system is pretty straightforward. It's just the momentum of the first sphere, m1 times v1, plus the momentum of the second sphere, m2 times v2. Simple as that. And after the collision? Well, remember they stick together. So now we have one object with a combined mass of m1 plus m2, and it's all moving at one single velocity, which we're just calling v final. And here is where the conservation of momentum principle becomes so powerful. We know the initial momentum has to equal the final momentum, so we just set our two expressions equal to each other. We do a little bit of algebra to get v final by itself, and we get this expression right here. And just like that, step 1 is done. Perfect. Now that we have our final velocity locked in, we can move on to the main event, finding out what actually happened to the kinetic energy. This is going to cover steps 2 and 3 of our game plan. Okay, step 2 starts with the initial kinetic energy. This part's easy. It's just the kinetic energy of the first sphere plus the kinetic energy of the second sphere, before they've even touched. And the final kinetic energy is just the energy of that single combined object. We use the same 1/2 mv squared formula, but now m is the total mass and v is that final velocity we just solved for. And now for the last step. That change in energy, delta T, is just the final energy minus the initial energy. Now, I'm not going to lie, the algebra here gets a little messy. You have to substitute that big fraction we found for v final and then simplify everything.
But trust me, if you work through it carefully, all that mess collapses into something surprisingly simple and, well, elegant. And here it is. After all that algebra, this is our answer. This one single formula tells us everything we need to know, the exact change in kinetic energy, and it's based only on the masses and the initial velocities of the two spheres.
But a good physicist never just stops at the formula. Now we need to understand what it actually means. What is this equation really telling us about what happened in that collision?
So, take a close look at this thing. Notice that negative sign sitting out front. And then notice that the velocity term in the parentheses, it's squared. What does that structure tell you about the final value of delta t? Could it ever be positive?
Well, the math confirms exactly what we suspected. Any number squared is always going to be positive or zero. And masses are always positive. So the only thing that can make this entire result negative is that minus sign right at the beginning. This proves that for any perfectly inelastic collision, the change in kinetic energy is always going to be negative. In other words, kinetic energy is lost from the system's motion. So let's go all the way back to our first question. Where did the energy go? Well, it wasn't destroyed. It was just transformed. It turned into the energy needed to permanently bend or deform the spheres. It turned into heat that was generated at the point of impact, and it turned into the sound of the collision itself. And that brings us to the final thought. This principle, it is not just some abstract problem in a textbook. It is absolutely fundamental to real-world engineering. Think about how car bumpers and crumple zones are designed. They are built specifically to have an inelastic collision. They're designed to transform all that deadly kinetic energy of a crash into manageable forms, like bent metal and heat, all to protect the people inside. It's not just physics, it's physics that saves lives.